Hello everyone and welcome back. Today we're going to continue our exploration of statistics and take a quick focus on how to deal with skewed data sets. To begin our discussion, we're going to review quickly what a log normal random variable is because it sort of motivates some of the concepts that we're actually going to be using to remove skewness today. So remember that y, if it is a normal random variable with a mean of mu y and a variance of sigma y squared, then if we define x to be the exponential of that normal random variable, then the resulting variable x is said to be a log normal random variable. And the probability density function of that log normal random variable takes the following structure. Keep in mind, if you do know the probability density function for y, i.e. the normal random variable, the only difference between it and the PDF for x is that it has x in the denominator of that leading coefficient term, and it has the natural log of x instead of x right there. Also note that these terms, mu y, sigma y, in those three places, are the mean and standard deviation of y, not x. Therefore, it's very important to interpret those terms not as the standard deviation and the mean of the log normal random variable, but rather the standard deviation and the mean of the normal random variable for which the log normal random variable was developed from. Okay, so those are just some of the basics of log normal random variables that you definitely should be already aware of. Now, let's notice a couple things that are very important. So notice that if x is defined to be equal to the exponential of a normal random variable, and let's again recall that if y is normal, then x is a log normal random variable. And if you look at the distribution of a log normal random variable, then you should recall that the distribution sort of looks like that. So every time we talk about a log normal random variable, one alternative interpretation is that that distribution is skewed to the right. So it's a skewed right random variable. And that's pretty much the perspective that we want to focus on here. So if x is a log normal random variable or a skewed right random variable, and we take the natural log of that particular random variable, and keep in mind, a log normal random variable is defined on the interval 0 to infinity, non-inclusive of 0. That means we can take the natural log of any of those numbers in x and not produce, for example, any undefined or imaginary numbers. So if we take the natural log of x, what will we get? Well, we're going to get the natural log of e to the power of y, but natural log and exponential of y are inverses, so we're just going to be left with y. And keep in mind, y is not a log normal random variable, but that is a normal random variable, but moreover, a normal random variable is not skewed right, nor it is skewed left. In particular, it is a symmetric distribution. So notice, if x is a skewed right random variable, we can sort of get the fact that if we take the natural log of that particular random variable, we should get something approximately normal or moreover approximately symmetric. All right, so that's actually going to lead us to the log transformations for skewed data sets, and that's going to actually help us reduce skewness in many of these cases. So now let's actually define some ways of describing the skewness of a data set. So definition. So the skewness coefficient, of dataset S, and we're going to denote this by Sk of S, is given by, so Sk of S is equal to, one of the most common ways to sort of interpret skewness is the relationship between the mean and the median. So remember, if the median is greater than, or if the median is less than the mean, then we usually have evidence to believe that the data set is skewed to the right. So if the mean is greater than the median, then that difference is going to be positive. So skewness coefficient positive, implying a right skewness, that would make sense. And of course, that usually is a big number. So usually dividing it by the standard deviation, giving us sort of like a z-score type of transform here, is definitely an appropriate, or one of the appropriate metrics for skewness. Now, there are other alternatives or other definitions out there that some people use. For example, some people will throw a 3 in front of it, so 3 times x bar minus the median divided by the standard deviation. Some people will also use the mean minus the mode of the data set divided by the standard deviation. Those are some other alternatives that you may encounter, but overall, or for the general sequence of data elements, they usually produce equivalent interpretations of the data set in terms of its skewness, but of course each of them have their pros and cons, but we're going to be working with this simple version in this discussion, just in case you are curious, and you can of course calculate these other two metrics and sort of see if you get possibly different or similar results to our analysis. So with this definition, what kind of things can we build? So if 1, the skewness coefficient of our data set is equal to 0, that means the mean is equal to the median. Therefore, we will define this data set as not skewed. So one can think of these as definitions. Second, if the skewness of S is greater than 0 based upon these definitions, then we'll say it is possibly, some people will say positively, skewed to the right. And 3, if the skewness coefficient is less than 0, then it is possibly skewed to the left. The only reason that I'm including these words possibly here is if you get a skewness coefficient of approximately equal to 0, like 0.001 or negative 0.005 or something very close to 0, sometimes it really is not very evident whether there is skewness or not. So you definitely need to be very, very careful when your skewness coefficient is equal to 0. Some people will even go the length of possibly defining some thresholds for the skewness coefficient. For example, if the absolute value of the skewness coefficient is greater than, I don't know, for example, 3, then we say the distribution is skewed, either to the left or the right, depending on the sign of the skewness of S. And that's pretty much where that 3 comes from in that first definition. And I'm just using this number 3. There's nothing super special about it. I'm just using 3 like 3 standard deviations from the mean in terms of the empirical rule, for example. But of course, when you're working with your own data set, you should have the maturity to develop your own threshold in terms of how large is a large skewness coefficient. So let's look at a numerical example just to see how we would go ahead and calculate that skewness coefficient. So examples, let's assume we have the dataset S given by the dataset 4, 7, 7, 9, 12, 16, and 27. So notice that we have that 27, which at least qualitatively appears to be an outlier. So it's possible if we look at a histogram of this data set, we probably have something that looks similar like that if we were to include, for example, replicas of each of these points. So we probably will get a skewed right data set in this particular example. So let's just calculate a few things. So you should already know how to calculate the arithmetic mean. You should be able to show that that's approximately equal to 11.71. The median of this data set can be found to be equal to 9, and the sample standard deviation for this data set is going to be approximately equal to 7.78. You can generate those values, for example, in Excel or R, or you can do them by hand since this data set is, subjectively relatively small. Once you have these 3 data values, you can calculate your skewness coefficient. So the skewness coefficient is going to be approximately equal to 0.3488. So based on our definitions, we do have evidence to believe that this data set is skewed to the right. One could of course argue that, it's relatively close to 0, but it is positive, therefore it has at least some small right skewness relevant in the data set. Now that we have some mechanisms in order to calculate the skewness coefficient of a dataset, now let us see if we can possibly remove the skewness from a dataset, or might possibly not remove but reduce the skewness of that dataset, or make it closer and closer to normal. So for the same exact example that we just did, remember that we got a skewness coefficient of 0.3488, which means we have evidence to believe that the distribution is skewed to the right. Of course, if we have a unimodal data set, and in this case we actually do, of 7, since we have a right-skewed unimodal data set, in some sense we also have evidence to believe that S is coming from a log normal distribution. So if S is truly coming from a log normal distribution, then if we take the natural log of the elements of that log normal distribution, we should get an approximately normal distribution, i.e. a sample data set whose skewness is a little bit closer and closer to 0. So if we define a new set called SL, which is just going to be equal to the natural log of the elements in that particular data set, Then we're going to get a new data set approximately equal to 1.39, 1.95, 1.95, which is the repetition of that 7, 2.20, 2.48, 2.77, and 3.30. Now with this new data set, I can calculate a mean, a median, and a standard deviation. So one can find that the mean of this new data set is approximately 2.29. The median is going to be equal to 2.20. And the standard deviation is going to be approximately 0.63. And from these elements, you can calculate the skewness coefficient of this log transform data set to be approximately equal to 0.1481. And as you see, the skewness of the data set has increased after we have taken the log transform. And what motivated us to transform that data set? Because the original distribution was skewed to the right. And since we have a skewed right distribution, that means we have evidence to believe that it's coming from a log normal distribution, and hence taking the logarithm of that data set should reduce the skewness back to sort of a data set that should, represent at least sort of approximately to a normally distributed data set, right? So now our distribution is less skewed, still skewed right, but less skewed than it was before. Now let's look at another data set and sort of see what we have going on here. So let's call it example 3. So we have data set S, which is equal to 1, 9, 15, 17, 18, 18, and 20. Now, what is the skewness coefficient of this data set? So I'll leave it to you as an exercise to, calculate the mean, median, and standard deviation, but you should find that the skewness coefficient of this is approximately equal to negative 0.4456. At least by our definition, that means we have evidence to believe that this data set is skewed to the left, not the right. Now, what if we take the natural log of these elements? Will we get a data set whose skewness is smaller? So if you define, for example, SL to be equal to the natural log of that data set, then you can calculate the skewness coefficient of that data set for this particular example to be approximately negative 0.4417. Now do notice that the skewness did decrease. In particular, it gets closer to 0 in terms of magnitude, but the skewness does not dramatically change anything in this particular sense. And in some cases, the natural logarithm of a skewed left data set will actually make the skewness worse than it was before. Okay, so at least from the logarithmic perspective, from the practical sense, the following principles should keep in mind. So logarithms do not necessarily fix or remove skewness for skewed left data sets and should only be used on skewed right data sets. Right? And that's a very useful property to sort of keep in mind when we're actually performing these log transforms on data sets. The next observation is actually going to be very, very useful to us. So let us assume we have a finite set S that contains elements x1, x2, down to xm, with the property that x1 is less than or equal to x2 is less than or equal to all the way down to less than or equal to xm. That is, the set must be ranked from least to greatest, with repetition, of course, allowed. So we can define the reflection of S, and we're going to be denoting that by S sub r, is going to be the set of new elements where those new elements are going to be equal to 1 minus the old element plus the maximum of the old data set for which we are reflecting. Now there are several definitions for which one can take to be the reflection of S. This is just one of the more simpler ones. For example, you can choose this one to be any positive number, for example 0.1, 0.5. You could even choose 50, but you'll see actually why we want this number to be 1. We're actually going to get some nice properties from this. Now, let's look at a couple analytical properties of this reflection data set for the general case. So if we consider the maximum of the original data set, which was by definition equal to xn, then that's going to go to where? So the new xk for that particular data set, it's not necessarily the last one, right? And actually you'll see that it's not. It's actually going to be equal to 1 minus xn plus the maximum of s, which by definition is xm. And notice that minus xn and xn will cancel, and we're just left with 1. So that means the maximum of our original data set is actually going to be mapped to 1 in our new reflected data set. And actually 1 can show that 1 is actually the minimum of SR, right? So the maximum is going to become the minimum, which makes sense in the realm of reflection. Now, is the range going to be the same? So let's look at the range of the new data set. So the range of the new data set is going to be equal to 1 minus x1 plus xn minus 1. Now, why exactly is this the range of the new data set? So think about it for a moment. So we already know where the maximum of the old set is going to go. The maximum of the old set is going to go to 1, where 1 is the minimum. So take a guess at what that is. Well, that is the result of the minimum going to a new set in the element. So in some sense, this is equal to the maximum of the new data set. So we have the maximum minus the minimum, which is the definition of the range, right? So if we subtract these two elements, what will we get? So the ones are going to cancel, and we're going to have xn minus x1, which is of course equal to the maximum of the original data set minus the minimum of the original data set, which is of course equal to the range of the original old data set. So the range has not changed. So that's at least a basic proof that the range is going to be preserved under reflections. More in particular, the variance of the reflected data set is actually going to be equal to the variance of the original data set. So that means the standard deviation of the reflected is going to be equal to the standard deviation of the original, right? Which is going to be a very, very useful property. Now, a couple other things that are going to be very, very useful in this analysis is to be the following things. So let us define. Actually, we don't need to define that. Let's just get into the calculations. So where's the mean going to go? So the mean is going to go to 1 minus the mean plus the maximum, and the median is going to go to 1 minus the median plus the maximum, right? So remember, in the skewness coefficient of S, that's going to be equal to x bar minus the median of x divided by the standard deviation of x, right? And keep in mind the standard deviation of x is the same as the standard deviation of x for the reflected data set, right? So that's not going to change. So what about the top? So the top is going to go to where? So the skewness of the reflected data set is going to go to 1 minus x bar plus xm minus 1 minus mx plus xm all over the standard deviation of the original, right? Which is the standard deviation of the new, because that's not going to change. So that's going to be equal to what? So we're going to have minus x bar there, because the 1 minus 1 is going to cancel. The xn minus xn is also going to cancel. And then we're going to be left with the median of x on the top divided by the standard deviation of x, which is going to be equal to minus x bar minus the median divided by the standard deviation of x, which is minus skewness of the original data set, right? So what have we proven here? So that means, and this is very, very important, so that means the skewness of the reflection is equal to the minus skewness of the original. So how can we apply this to the practical sense? That means if S is skewed left or right, then that means the reflection is going to be skewed to the right. And if it's skewed to the right, that means we can apply the log transform in order to reduce the skewness of that data set. So let's bring back this old example that we were talking about just a moment ago that actually wasn't skewed to the right, but rather it was skewed to the left. In particular, its skewness coefficient was approximately equal to negative 0.45. So if we were to reduce the skewness of it, taking the natural logarithm doesn't necessarily do that. So what we can do is we can reflect this data set and then take the natural log of the reflection, and that should reduce the skewness of that newly transformed data set. So what are we going to do? So our reflection transformation is given by our new values in our data set is equal to 1 minus the old values in our old data set plus the maximum values in our old data set. And keep in mind the maximum value is going to be equal to 20 in that particular data set. So for this particular example, we're going to have 1 minus xk plus 20, which is going to be equal to 20 plus 1 minus xk, or 21 minus xk. So you can do 21 minus 1, 21 minus 9, 21 minus 15, all the way down to 21 minus 20, which is going to give us 1. So our newly reflected data set, SR, is going to be equal to 20, 12, 6, 4, 3, 3, and 1. So that is our reflected data set. Now let's look at a couple metrics in terms of S and SR, so we can sort of summarize some of those theoretical properties that we were talking about just a moment ago. So we're going to analyze the mean, the sample median, the sample standard deviation, and also the skewness of those particular data sets. So let's look at S and also SR. All right. So what are those going to come out to? So we actually already calculated the mean, median, standard deviation of skewness already, or we should have. So that's going to come out to 14, 17, 6.73, and approximately negative 0.4456. Now, will the mean and median change? Most likely they will. Let's assume that that this reflection is actually correct, then you should find that the mean and median should be 7 and 4 respectively. And what about the standard deviation? You should know that that's actually going to remain the same. And what about the skewness? Without calculating anything, what should that be? So notice that that's actually going to come out to 0.4456. So let's just analyze this analytically. So the standard deviation is going to be the same as before. These are going to be opposites. Now, although these two metrics, the mean and the median, are the same or are different, they do have the same difference, right? So 17 minus 14 and 7 minus 4 are both equal to 3. Okay, so they're not completely different. They still have the same distance. They're just in different locations, in particular reflected locations. Okay, so now that we have a skewed right distribution, now what are we going to do? Now we're going to define a new set. It's going to be the log of the reflection, right? So that's going to be the log of the reflection. So if we take the natural log of those reflected data points, then you will find that the skewness of SRL is actually going to come out to approximately 0.1665, which is substantially lower than what it used to be. So therefore, we have achieved our goal of reducing the skewness. Now let's consider this little set we have here. So one can calculate the mean, median, and standard deviation and find that the skewness of this data set is going to be equal to approximately negative 0.5820. Therefore, we have evidence to believe that the population this was sampled from is skewed to the left. Now, these negative values may pose a concern to you at first, but you're actually going to see that actually doesn't change anything, at least for this particular scenario, because this is a skewed left distribution. So our goal is not to take the natural log of these data points at first anyway, because taking the natural log of a skewed left data set isn't really going to fix any issues. So we're just going to go ahead and perform the reflection of this data set. So again, SR is going to be equal to 1 minus the original set plus the maximum of the original set. And one can find that the skewness of the reflection of that data set is going to be approximately equal to 0.5820, which, keep in mind, is a skewed right data set. And now let us actually talk about what's going on with these negative values. So where has negative 14 gone? So in this little transformation, we have our newly transformed data set. So let's look at minus 14 in focus. So that's going to go to 1 minus negative 14 plus the maximum value of S, which is going to be equal to 5. So that's going to be 15 plus 5, that's going to be equal to 20. What about negative 1? So negative 1 is going to go to 1 minus negative 1 plus 5, and that's going to go to 5 plus 2, which is going to be equal to 7. So all these negative values have been mapped to a positive number. Well, what about the other spectrum of these things? So if we look at the extreme value, 5, remember 5 is always going to go to 1, right? We already know that to be true, right? So in general, even if xk is less than 0, so if xk is less than or equal to 0, this transform, this reflection transform, is always going to map to new values that are greater than or equal to 1, which is very, very good. That means you do not have to perform, for example, a horizontal shift on your data set, which is actually pretty great. So now let's get back to our original example. So we originally had a skewed left data set, and even though it had negative values, we just simply performed our reflection, and that's still going to give us a non-negative data set, in particular an always positive data set, since it's always greater than or equal to 1, so of course never equal to 0. Therefore, we can perform our log transform on our data set, and what is that going to give us? So one can find that the skewness of the log transform of our reflection is going to be approximately 0.3453, which is of course less than the skewness of the reflection and the original data sets that we had. Let's consider this last data set to close things off today. So let's assume we have negative 7, negative 5, negative 2, 1, 6, 10, and 16. So as usual, one can calculate the skewness coefficient of this data set, and one will arrive at a number approximately equal to 0.3315, which implies that we have evidence to believe that S is coming from a skewed right data set. So what do we usually do to skewed right data sets? Well, we usually just take the natural logarithm and that reduces the skewness, right? But we have a little bit of an issue because we can't take the natural log of negative numbers and also 0, even though 0 is not one of our issues, at least in this particular example. So we can't just take the natural log of it. Well, what about reflection? Because reflection will remove the negative numbers, but if we reflect it, yes, it fixes the negative issues, but we also get a skewed left distribution, which logarithms don't perform on, right? So reflection isn't the best choice of this particular issue in terms of remedies, right? So what we're going to do is we're going to define a shifting operation. So the shifting operation is going to be defined to be equal to 1 plus s minus the minimum of s. Okay, so what exactly is that going to do? So if we look at this from the theoretical perspective, that means our shifting operator is going to take x1 and send it to where? So that's going to take x1, which is going to go to, so let's look at x1 in particular. So x1 is an s, and x1 minus x1 is going to go to 0, and that's going to give us 1. So that means if x1 is the minimum of our original data set, that's going to be mapped to 1, which means all values in S are also going to be greater than or equal to 1 because we're simply shifting this to the right. Right? So if our data set is sort of scattered here, so 1, 2, 3, 4, and 0 is located there, that means this is going to be mapped to 1, and then we're going to have the other 3 values sort of located right next to it. So it's going to sort of march one to the other. Okay, so the shifting always removes the negative numbers, and also, in particular, because the range is not going to change, just the position of the elements are going to change, the skewness of S and the skewness of the shifted version of S are always equal to each other, and I'll leave that to you as a proof. That's actually not too difficult. So the shifted version of S via this transformation, so 1 plus an S minus the minimum of S, where the minimum is going to be equal to negative 7. So minus 7, that's going to be plus 7. So 8 plus every element in S is going to give you our new data set. So 8 plus minus 7, 8 plus minus 5, all the way out to 8 plus 16. That's going to give us our newly shifted data set. In particular, 1, 3, 6, 6, 9, 14, 18, and 24. So One can look at the skewness of this. So the skewness of the shifted version of S is going to be equal to approximately 3.3315, which of course, as I mentioned, is the same as before. And since we have all positive numbers and we have a skewed right data set, therefore performing the log transform of the shifted data set should remove the skewness. So let's sort of see what that comes out to. So that's going to be the log transform of the skewness. So let's call that SSL. And it's going to come out to approximately negative 0.0446, right? Now, you may be scared because notice that the skewness coefficient is negative now, right? And you're going to be like, well, it's a little bit awkward. So in some sense, what it's sort of saying is that this number is sufficiently close to zero, right? So the skewness is sort of, around symmetric, not really super skewed right, but, a little skewed right, right? So when you take the log transform, sometimes it will produce the opposite number, but in terms of magnitude, notice that 0.3315 has changed to, at least in absolute value, to 0.0446, which is definitely a lot smaller than it used to be. Yes, we have transformed it into a skewed left data set, but the skewness is less, right? And that's, pretty much every scenario that you could come up with in this particular scenario. So let's just outline the log transform and those steps, okay? So let's assume we have a original data set. So the very first thing we need to do is calculate the skewness coefficient of that data set. So from the skewness coefficient, we ask ourselves, is that skewness coefficient greater than 0? If it is greater than 0, we need to ask ourselves, does it have negatives? If no, then we can just take the natural log transform. So we can take the natural log of that data set, so ln, and that will remove the skewness, and life is good. If it does have negatives, that means we need to perform a shift. And once we perform a shift, then we can take the natural log. And if the skewness coefficient is negative, then we can reflect it. And since it's reflected, it's never going to be negative. So then after it's reflected, we can take the natural log, and we should have reduced skewness. And this is what we refer to as the log transform of a data set. Transform. Okay. Now there are a couple other alternatives to the log transform, and I'll just briefly mention them here. We can talk about them in another episode, possibly. The other one is what is known as the square root transform. And the square root transform has pretty much the same exact flow in terms of how the log transform does. The only difference is you can take the square root of 0, where in the natural logarithm scenario, you can't take the natural log of 0. So square root transform sometimes is usually a little bit easier to deal with. Again, you can have negative numbers with it. It also produces imaginary numbers. But for the most part, the square root transform is very similar to the log transform, just usually not as robust as the log one. And a more advanced method is known as the box-Cox transform. Now, the box-Cox transform is a more generalized version of the natural log transform, but it requires a little bit more maturity in terms of the tools because it requires you to optimize a particular functional, which we'll definitely talk about later once we've talked about regression with a little bit of time, right? But for now, the log transform can reduce the skewness. Just make sure you map back to the original domain with, say, confidence intervals or p-values if you want to interpret them in the correct way, because once we transform our domain, we are in a transform space, not the original space, right? So if you have blood pressure and you take the natural log, we have natural log blood pressures or logarithmic blood pressures. Usually they cannot be interpreted in the same exact way. So you would have to exponentiate to sort of go backwards if log was the only thing that you did. But that's how we usually, at least in the elementary sense, deal with skewed data. I hope you enjoyed, and I'll see you in the next video. Take care.